let's get started looking again at what this chapter is about. It is a nice setup. It is a little bit different to the way we used to do things, in which we just jumped straight into mechanism, and that was usually a bit of a disaster. This at least gives people some sort of idea of what we're going to see for the rest of the 2 semesters. This idea of how chemical reactions work. And if you're a scientist or an engineer, I think one of the fundamental reasons we do what we do is because we like to know how things work. So we'll take this stuff in fairly sort of simple, gentle steps, and we'll build up, and we can extrapolate into biology, we can extrapolate into polymer chemistry and stuff like that for the engineers, and it becomes very useful because you can predict things. Organic chemistry is a marvelous subject because you can make new stuff simply by following the rules and being creative and putting the molecules together in different ways. You can make new medicines, make new materials quite quickly, and that's difficult in other subjects. I mean, can you do new physics straight off? Probably not. Most people can't do physics anyway, right? Doing new physics is way beyond. Can you do new biology? Can you create something in the lab straight away? Probably not. You can in organic chemistry. So we need to start thinking about how the rules have developed, how the constraints have developed, what the language is, to be able to discuss chemical reactions by mixing starting materials together to give products. And that will extrapolate very quickly into biological systems. So we talked about 2 words that you need to be happy with: enthalpy and entropy. So enthalpy is typically about energy, bond energies, things like chairs and boats and stuff like that, eclipsing energies. And we can talk a little bit about bond energies as we work our way through. Again, I'm not going to ask you to memorize a whole bunch of numbers, that's pointless, but have an idea that if you heat something up, a weak bond will pop before a strong bond. That's fairly simple. We talked a little bit about the other thing, which was entropy, and that tends to be a little bit misunderstood. Again, it's about energy, it's about displaying or sort of expressing degrees of freedom, if you say. Rotations are always good. If the molecule is constrained, it has less entropy, so cycles tend to be disfavored in this sense, and the acyclic system tends to be favored because the acyclic system has more opportunity to do this, right? It can rotate in more directions and express itself. So this sort of language builds into the Gibbs equation. I hope you've seen this before. I know the general chemistry system or sequence can be a bit sort of haphazard sometimes when people don't see everything that I'd like them to. But this governs what we do. This equation here governs what we do, and it will be able to tell us whether the reaction is viable or not from a very simple ground-up method. So delta G, and I think the key here is delta, the changes, the difference. And the delta G being the changes in energy, entropy, enthalpy, from the left-hand side of a reaction with the starter materials to the products on the right-hand side. Now, we have done some of this with acids and bases, and I've asked Tyler, for the 2 of you who show up to SI, and the 3 of you who come to my office hours, we'll talk about this in the context of acids and bases. So we've done acids and bases, and we can use these words now to extrapolate and talk about that. We need to be happy with what delta H and delta S are. We need to understand that temperature plays a role here, so we will be talking about, doing reactions in the lab. Why do you heat things up as we work your way into experiments in the near future? Why did you heat this one up? Why did you cool this one down? And think about it in a sort of a holistic sense so that you understand what you're doing in lab. So the delta is important. The changes are really important. And this now branches off into 2 different disciplines. Have you heard the term thermodynamics before? Have you heard the term kinetics before? Yes. Okay, so people are going, yes, that's a good thing. We're going to talk for most of today about the differences and talk about parameters that allow you to decide whether a reaction will work or not, whether it's viable or not. Is it too slow to work? How do you speed it up? Is it energetically favorable or not? Can we make these things work? So if you want sort of a summary very quickly, thermodynamics, as far as we're concerned, is really going to be talking about systems in which there might be an equilibrium and you have to decide which side is more stable. And we did that. We did K is greater than 1, K is less than 1 for the acid-base chemistry, and that was often based on things like resonance stabilization. You think about the properties for acids and bases. What made a stable conjugate base? Having electronegative atoms bear a negative charge. Having sp bear a negative charge rather than sp3. Stuff like that. Resonance. All that material. Those are thermodynamic properties. When we talked about the equilibrium cyclohexanes, having something axial was worse than having something equatorial. And we had the going backwards and forwards in equilibrium between different chair forms. That's all a thermodynamic type of idea. What we haven't spent a lot of time on yet, and you need to be happy with, is the idea of how fast things happen, not just in chemistry, but in biochemistry and biology. So kinetics will be the height of reaction barriers. It will be the activation barrier in a system. And we'll talk about very simple ideas that will dictate the height of that barrier. Sometimes that barrier is too high and the chemical reaction won't work. Sometimes we can speed it up by adding a catalyst. Sometimes it just won't go. So this is a gentle chapter. There's a lot of detail here, but some of it you've seen before, and I want to make sure you see it from my perspective as an organic chemist interested in the bigger subjects. So these reaction profiles will become part of your life irreversibly. Yes, you will get to like and you will get to know reaction profiles and you'll get to use them. And we'll be able to say that in these examples, we'll be looking at some starter materials on the left and some products on the right. So A plus B gives C plus D, just a generic example. Now we need to worry about which is more stable, using the principles that we've already developed, plus some others that we'll see. You'll see in this example, which is more stable, CD or AB? CD, right? It's lower on the reaction profile in terms of free energy. Now this at the bottom, called reaction coordinate, this is something that often is misunderstood. It's not time. It's not the progress of time. It's the progress of bonds forming and bonds breaking. Because in this reaction, A and B have to do something. They have to change chemically, and that involves bonds forming and breaking to become C and D. And as we go up these reaction profiles, you have to recognize that, this is like calculus. Every time you hit a point on this line, there's a little difference. There's a little change in what's happening in the system. And we'll start drawing the reaction arrows today, the curved arrows, to show how electrons are pushed around, and we'll talk about what's at the top of this reaction profile. So there's a lot to come today. Ask me questions as we go. Be happy with this now so that we can start to use it, because when we get into 7 on Monday next week, it really is a big, big subject. So what we're saying here is that this delta G difference between A, B, and C, D is going to drive that reaction. And you've probably been told in the past that if delta G is negative, the reaction goes, right? You can do a spontaneous type reaction. What you should be concerned with now is that a lot of these reactions will go backwards. So that's where we use these guys, right? We'll use those equilibrium arrows, which we have done a little bit. And we said if we had a massive difference in pKa, maybe only one side was favored. And if we had a massive pKa in the wrong direction, maybe the left-hand side was favored. But in most of the examples we dealt with, we had this situation where maybe the left was a bit more favored than the right. You've seen this before. What you haven't spent a lot of time on, I don't think, is this activation barrier. We'll talk about the height of that thing. We'll talk about how to get over it. Some systems will have to differentiate which molecules will go over, which won't. We'll see in chapter 7, chapter 8, 9, 10, the rest of it, splits in which some molecules go in this direction, some molecules go in that direction, based on some fairly complex principles. So the height of that barrier will dictate how fast things are, and we'll start off with thermodynamics, and then we'll talk about kinetics. So thermodynamics, looking at the geography of this picture. Thermodynamics is all about this level, and it's all about this level, and their relative values. You want to be more stable. You think about that in the context of cyclohexanes. You wanted your large groups equatorial. That's exactly the same thing. You could plug in a cyclohexane here and a cyclohexane here, and even though that's not a chemical reaction, you do have this equilibrium idea. You could plug in acids and bases here. This could be an acid and base, could this be the conjugate base and the conjugate acid, and you get the same principle. You're going to go to the more favored stuff. So we can think about equations. I'm not going to ask you to calculate these things. You've already done this. You can leave your calculators at home. You've done enough of that in the past. But an equilibrium constant now is a useful measure and a useful guide as to whether things will work or not. And if we get going backwards and forwards for an equilibrium, which side will be favored? Because many of the chemical reactions you have to deal with in the near future, once you mix from a flask in the lab, you haven't done this yet, you will very soon, once you mix two materials, at the very instant they mix, you just have those starter materials. And then over time, things start to change. They start to see each other. They start to decide, I want to react. Let's react and make some products. And then those products have the opportunity to go backwards. We saw that with the acids and bases. So you make the conjugate base, the conjugate acid, it can come back. And we need a measure for which is favored and how to be able to think about what comes next, because often we'll do something after that. So what we've got here are the concentrations of C and D. In other words, the concentrations of the products divided by the product of the concentrations of the starter materials. I just put this in here to use the organic chemistry language. The product is what you get out, hopefully, and the starter materials are what you put in. You have not done that yet in lab, but that will become a major part of what you do in that class. So the equilibrium constant here is a measure of how much you have, which is favored, products of starter materials. And if you had to tell me K for this, is it greater than 1, less than 1, or about 1? It's greater than 1. If you don't see that, yeah. Okay? Yeah, because this is all dependent upon understanding these ideas. So this example here is all about how much you have, and we tend to use this term. This term is simply just saying how much of each you have. The populations of the materials on the left and the right can be measured by an equilibrium constant, by different techniques, some of which you've done, some of which we'll do next term, but it's all about how stable things are. You typically want to go to the stuff that is the more stable material. That's fairly obvious. Questions so far? Joe?
So the y-axis here is free energy. It shows the change in delta G. Is that also the change in delta H?
It's balanced. It's a balance, isn't it, between delta H and delta S? Because any delta G calculation involves both of them.
would that say, like, the products weren't like practically the same? Would that not be a measure of delta G?
We'll be looking at that a little bit later. In this example, delta S is 0, isn't it? Because you've got 2 to 2. So delta S isn't a problem in this. We'll go case by case and point that out as we go. Okay, but this is a huge universe, and we're about to dive into it. Are we okay at the back? Are we awake? Very good. All right. So we can relate delta G to the equilibrium constant, and I hope you've seen this equation in the past. I'm not going to ask you to derive it. I'm not even going to ask you to do any calculations with it. I just want you to understand from today that the difference in the free energies here dictates the equilibrium constant. So here, K is going to be greater than 1 for this system. And beyond that, understanding what's going on in this flask. I have mixed A and B from 2 bottles in the lab, and I'm producing C and D. At equilibrium, which do I have more of, C and D or A and B? C and D. Now, this particular barrier isn't that high. So if that barrier isn't that high, I can go backwards. Think about acid-base reactions. A lot of those were reversible. I can go backwards. So you're constantly going backwards and forwards, and at equilibrium in a system like this, you will have some of this, and you will have some of that. That complicates things massively, especially in the second semester. In some examples, if I had a situation like this, let's exaggerate it. If I started here with some reactive species and went down to here with some stable species, do you think that's going backwards? Probably not. There's such a big difference here in delta G that the products are so much more stable, they won't go backwards, right? So those are the types of things you've got to see and got to understand as we work through here. Right, okay. Tables can be useful, they can be, put people asleep, but I think this one's kind of important. What does it take to get a reaction to go to completion? What does it take to get a reaction to go all the way to the products and not come back? Well, it takes a difference in energies, in what you start with versus what you make. And it turns out it doesn't take that much of a difference. If you look at this with kilojoules per mole, you look at the 17 here. 17 kilojoules per mole difference in the materials on the left and the materials on the right give you pretty much completion, okay? In which all of one side has been consumed and all of the other side is now there. This might be the starting materials, might be the products, depending upon how stable they are relative to each other. But now we have a situation in which, yes, that delta G can be measured, and we can put an equilibrium constant on it, and then we can say for sure, at equilibrium, when this reaction is settled, all of it is the product, or all of it is the starting material. And the job over the next few weeks is to work out how to manipulate this. How do we make things go that are sluggish, that don't want to go, and how do we set up real reactions? So you think about what we did here. Any examples of where we did this? Did we do an equilibrium constant of 1? Because that suggests if you have an equilibrium constant of 1, you have both sides equal, right? When did we do equilibrium constants of 1? Okay, yeah. When you reacted an alcohol with water, or an alcohol with an O minus, yeah? An alcohol with hydroxide. 16 on this side, 16 on this side. What we're trying to get over to here is that we have done some of this already. We've got thermodynamic numbers that we can use from the pKa values. For those of you who learn them, you can now use those things to discuss this idea. Yeah, so we're not doing anything particularly new there. So be very careful here. These graphs will become much more complicated as we work into some real reactions. But right now, very sort of gentle introduction. This difference is what governs the equilibrium constant. And the bigger that difference, the bigger the equilibrium constant. Easy enough? If there is no difference here, if I have a graph here where they seem to be equal, what's the equilibrium constant approximately? 1. Can't have a 0, even in Youngstown. Okay, it's going to be 1. So again, this is a lot of general chemistry. We try to take our time on this so that everybody's on the same page, having had different people for that class. What I've just done to finish that off is I've talked about free energy. I've talked about the relative energy of what we start with versus what we get. And through principles, some of which you've seen, like resonance, induction, all that kind of stuff, you can already make opinions on this. What we move into now is how fast things happen, kinetics. So thermodynamics was about, if I do this again, thermodynamics is about the horizontals, kinetics is about up here. It's a little bit different. Kinetics is how fast things happen. And you have to get conversant with this quite quickly because we're going to talk about different rates of reaction, different orders of reaction, and what is the reaction dependent upon. We're going to have a series of steps in a process in which one is much slower than all the others. And that slow step will dictate how fast the reaction goes. All the other steps will be irrelevant because they're fast. So we've seen this before, I hope. We can say that the rate of reaction is related to what's known as a rate constant. and the concentration of the starter materials. I think this is the most important thing, the concentration of the starter materials. I'll start very quickly by saying, if you want molecule A and molecule B to react to each other, is it fair to say they have to find each other at first? Yes? Now, if you take a salt, molecule A, and a salt, molecule B, and you put them in a reaction flask and that's it, nothing will happen, right? They don't have a medium to swim around in to find each other. It's like diving into a swimming pool that's empty. You're not going to be swimming. You're going to go to the hospital. You need, in most organic chemical reactions that you need to deal with, you need a medium. In biology, what's the medium? Water. That's the solvent in biology. That's where we go later. You need to dissolve things up. Why? So that they become dissolved up and they can start swimming around. They can find each other. Fair enough. If you take a tiny amount of these materials and you dissolve them up in a flask the size of this room, how long do you think it's going to take for these things to find each other? It's going to take a long time. Yeah, that might be a slower reaction. If you concentrate these things, put them in as little solvent as possible, where you increase the chance of them finding each other, you expect a faster reaction. Yes? So is it fair to say that concentration has something to do with how fast things happen? Yes, absolutely. So the concentration of the reactants here is really important, and it will lead into, in chapter 7 on Monday next week, a very subtle difference in how, let's say, one type of alkyl halide goes over here, and another type of alkyl halide goes over there. Or another alcohol goes this way, another alcohol goes this way, based on very subtle structural differences. So if we have a system in which only maybe one of the starter materials, the concentration of only one of the starter materials is important, you'll get what's called a first order rate equation. This seems a bit mysterious. Surely if I'm reacting A and B, I need B in there. Not always. B doesn't necessarily get involved in the slow step. We'll find that the slow step governs how fast things happen. And let's say A breaks apart. Let's say A has to break apart first, and then B gets involved. And that breaking apart is slow, where A collapses into ions, something like that. And then B gets involved, but B is not involved in the slow step. So you can get something called a first order rate reaction, in which A and B can react, but B is not really needed until the second step. This is one you're familiar with. You have seen this, right? You see very few of these. We might see one, maybe two at very most, and we'll be careful how we do that. Second order rate reactions and first order rate reactions, they are the ones you will be concerned about for the most part in this class and in biochem. Have you seen a second order reaction? Have you seen a reaction in which molecule A has to find and hit molecule B to go to the products? Yes, you have. What is it? Acids and bases. You think about the arrows for acids and bases. Base goes after the acid and takes off that proton. That's a system in which both have to be present for that to work. So therefore, that's a biomolecular reaction, as we'll call it later, and it's second order. The rate of reaction depends upon both the concentrations of both pieces. You need them both there to happen. This is quite rare, and the reasons it's quite rare is because it's quite difficult to get 3 molecules lined up all in one go. All right? So we'll not spend a lot of time on that, but we will spend a lot of time on these first two. So if I ask you this question, I have a reaction between A and B, and we don't know the pathway yet. We don't know how this works in terms of the things collapsing and changing to go to products. If I have a first order rate equation here, if I dump in more B, if I take more B and I just take the bottle and keep pouring B into this reaction, will it go faster? No, because the reaction rate is not dependent upon that B. Something has to happen to A independent of B for this thing to go. So you can put as much of B in as you want, and it still won't go any faster. Now, if you take this guy and you do this, let's say it's a second order reaction. If you put more of B in, does it go faster? Yes, because it's dependent upon that concentration. If you put more of A in, it goes faster. So it's a very subtle difference between the two systems, which we'll put in a lot more detail next week, and you'll see where this comes from. But be comfortable with the idea that the rate of the reaction, how fast things happen, is dependent upon the concentrations of what you've got in the flask. Joe? You'll see it next week. You'll see the SN1 next week, in which the SN1 differs from the SN2. Did I mention SN1 and SN2 already? I didn't say that, did I? I didn't say that yet. I just did. There are reactions next week in which the pathways diverge depending upon the structure of this guy versus the structure of this guy. One goes in a unimolecular sense, one goes in a bimolecular sense. Great stuff. So we've got some definitions. Again, hopefully we're all getting on the same page from general chemistry. And then we can start talking about this guy, the activation barrier. What does it mean? How do you can't really measure these things yourselves, but you can discuss which should be a faster reaction, which should be a slower reaction, based on some fairly simple principles that we'll give you. On the left, it is the same reaction profile we did for thermodynamics, no doubt. In thermodynamics, we talked about this energy and this energy. That's not the case here. In this graph, we are talking about the height of the barrier from the reactants to the top of that graph. And that is the activation barrier. And how high that thing is dictates how fast the reaction goes. If it's a high barrier, what do you reckon, slower or faster? Slower, low barrier, faster. So it's like roller coasters, right? It takes a long time to get up there. So you think about how high this is, you're on the roller coaster, you get to the top, it's slow, it's slow, it's slow, and then it's, oh, bloody hell, whoa, all the way down to the products, okay? Really fast. So how fast this thing works and how fast the reaction, the reaction rate is dictated by how fast or how high that barrier is. Why is it higher in certain situations than others? That's what we need to learn. Those are the principles we need to pick up, but they're not particularly complicated. So I put this chart up. I'm not sure this is from this textbook, but it's a useful graph. I'm going to say this very carefully, which usually means it's important. Not all molecules in a system have the same energy at the same time. It's written at the bottom of the screen. What does that mean? It means there's a distribution. It means if you have a mole of molecules and you put them into a flask, they're not all the same in terms of their energy. It's spread out. There's a distribution. It's like grades in a class. You know? You get some people who just want to watch their computers all day and they get Fs, and you get some people who want to text their friends all day and they get Ds, and you get a lot of people who are doing really hard work and just trying to get through the class and they get Cs. And then you get some of these people who get Bs because they really know what they're doing, and you get the occasional A. Yeah? That's how it spreads out. It's like a curve in a class. Well, most molecules have an average, and this average now is going to be important, because if not all molecules have the same energy at the same time, not all those molecules go out over these reaction barriers at the same time. Go back to that previous slide. There's my reaction barrier. If most of my molecules have a low amount of energy, they're going to be here. If some of my molecules have higher energy, they can get over that barrier. And then what happens is, this reaction tends to be exothermic, right? Energy is released, which can then feed back into the system and help more molecules get over that reaction barrier. And if you want all your molecules to go over that reaction barrier, what's the simplest thing you can do in the lab? Heat it up. It's as simple as that. You heat things up, and what that does is it changes your average energy of the molecules. So heat here is very important in terms of achieving those barriers. Most molecules have a low energy. Some have higher. It's a distribution. You do have an average. And as long as the average is okay and it's enough to activate or enough to go over that activation barrier, the reaction will go. So now we have, I've already asked this question, but here we see. Low activation barrier, faster rate. High activation barrier, slower rate. So if you can see that easily, it's easy to see with the graphs, how do you speed a reaction up? Heat it up. The simplest way to speed a reaction up is to heat it up. Later on we'll see catalysts, we'll see light and stuff like that, but right now the easiest way to speed things up is to heat them up. Give them more energy, make them bounce, make them vibrate faster, make them more aggressive, make them more reactive, and away we go. We get over those barriers. So we'll find out very quickly in the next chapters that some molecules can go in this direction and other molecules have to go in that direction, dependent upon their structures. Fair enough? Go. This one right here. So you have shifted the average temperature to a higher temperature. So more molecules, after you heat the system up, more molecules have more energy, so they can go over that barrier faster. It's like drinking coffee. Anna Maria, what's that in your hand? It's a huge cup of coffee. You've worked out the secret to college, haven't you? You've discovered coffee. Well done, I'm very proud of you. Very good. So we don't have to use electricity or bouncing beach balls or anything like we did in recitation, no, okay. Does this graph make any sense? You want things to go faster, you heat them up. That's all it is. Well, here's one of the principles. This is just a taster to get started. This is going to be in great depth next week. Why should certain molecules want to react faster, and why should certain molecules want to react slower? Well, one of the simplest things here that we can talk about is something called steric environment. Sterics. It's a big deal. It's kind of a big deal. Haldeman, I've got your money. Kinetics now is dependent upon things like environment. Where are you trying to go? If you're trying to go, if you're trying to get everybody out of this room and the doors are tiny, it's going to be a slow reaction, right? So how do you make people get out of here faster? Open up all the doors, knock the wall down at the back. Open things up so people can get out there faster. Well, this is kind of similar when chemicals react. If I have some species here, let's call it Nu because that's the term we'll use later, and I make it negative. The next chapter is all about negative things attacking carbon, which has a delta positive dipole. And I want to try and get here. So my mechanism is going to involve that going in and kicking out some species that can take a negative charge. And we've seen that. That's an acid-base reaction, essentially. One negative thing going after a delta positive thing, kicking something out. And if I want to think about that in a realistic sense, I need to think about these large molecules, these space-filling models. And I'm asking that Nu thing to attack this carbon and for this thing to break off. And what we're doing in this series, on this chart, is to put an extra methyl group on there. We are swapping out a hydrogen, and we're replacing it with a CH3. Do you think it's easier to get here now or harder? Harder. Yeah? You've crowded it out. You're starting to crowd out the place you want to go. So therefore, it's going to be harder to get there. That entails a slower reaction. If you go to the isopropyl system, we've got two of these big methyl groups, and again, the small models there don't really help, but this does. Look at that. It's really starting to get crowded there now. That's a much slower process. And if you put the T-butyl group on, it just isn't going to happen. You can't get there. So we'll find in chapter 7 very quickly that we get one mechanism for these guys. This one can do both, and this one does something different, simply because the reaction is too slow for it to be bimolecular and be attacked. So something else has to happen. What will happen is what I said earlier for the unimolecular thing. Something will break apart. Maybe that molecule will break apart first, then something else happens. So in the definitions here, steric is so far how crowded things are. You're getting more crowded progressively as you go across that series. So the reactions of that nature, where something is trying to attack that central carbon, will get slower. So steric bulk, B-U-L-K, steric bulk, tends to slow things down. It will a lot throughout the 2 semesters. Ashley, you're very quiet. Keep it that way. Okay. How else do you speed things up? Catalyst, right? Coffee, catalyst. You have some chemical reactions in biochemistry that wouldn't happen without a catalyst. They're just too slow. We do the same thing in industry. We do the same thing in chemistry. We need to develop catalysts. And there is an awful lot of this stuff to come. And the simplest catalyst you'll get to see is H+, which is everywhere. But now what we can say is that if I have a slow reaction without a catalyst, and I can work out some method to make it faster by adding, I don't know, a metal, a proton, something like that, I'm going to change the mechanism. The mechanism here is one step. This catalyzed mechanism is multi-step. What do I mean by multi-step? I haven't mentioned that yet. Multiple hills, multiple barriers means multiple steps. So you've made the reaction more complicated, but you've made it faster because you went a different way. Okay? If you're going to go, if you live in the south of the city, you drive down maybe 11, and maybe 11's got all the roadworks in it, and you want to do it faster, go someplace else. Change the scheme, change the direction, change the same outcome, you get the same place, you get home, but change the way you do it, in this case by adding a catalyst. Marissa, you okay? Yeah? Okay. A lot of that to come. So these energy diagrams, I think this slide just sort of tidies it up and brings it all together. You have 2 different things to think about. Thermodynamics, how stable things are. And, if I've done, I think, 16 or 17 lectures so far, and I've got 50 or 60 left. This is in about every class. This idea is in about every class from now on. How fast things happen is how high that barrier is. That barrier is often dictated by accessibility. If what you're trying to attack is accessible, it will be fast. If what you're trying to attack is inaccessible or blocked, it will be slow. Fairly simple. So kinetics is not to do with these guys here. These horizontals here, that's to do with thermodynamics. That's to do with how stable things are. And how stable things are when you get to those products dictates how much you have of it, and then dictates the equilibrium constant. So there's a lot of information there, and we'll have to get very good at drawing these things. I'm quite demanding with this. I want you to be able to draw these things at the top too, when we start there next week. A lot of detail, very little memorization, just understand it. Understand it, you can do it, and you can start to use it. Okay. Well, I think it's fair to say that organic chemistry is complicated, right? It's a different, there's a reason there's a 3 at the front of the class and not a 1. And part of the issue is we have to set you up for going other places. But we also have to give you a good, thorough understanding of what's happening in just basic chemical reactions, not necessarily biochemical, but chemical reactions. And you will see instances throughout the course, and I'll point them out, and we'll see the graphs, in which you get divergent pathways. And where we've done so far, A plus B gives C plus D, very soon we'll have to get to A plus B gives C plus D plus E plus F plus G plus H, blah, 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 blah. Right? And when we do get those products, there are governing rules that will say, I get more of C and less of D and less of E and less of F. It's very complicated very quickly. Because you can imagine chemical reactions can, depending upon what the structure of the starting materials would be, they can break, they can combine, they could break and then combine, they could combine and break. There are lots of different things that can happen here in terms of the actual mechanics. So these two graphs are trying to show you some of the things to come up in the near future. I'll point them out as we get there, in which A and B are mixed, and you get mixtures of products. And it's more complicated than simply C plus D. We're going to have to start talking about something called major and minor. We try to avoid numbers, but we do have some foundation governing principles that will allow us to say some of these products will be formed more so than the others, based on stabilities maybe, or based on how fast things are happening. So let's look at this. We have two pathways. A and B can combine to go over a barrier here and form C plus D. Or, through a different pathway slightly, A and B can come together in a higher reaction barrier to give products E and F. Now, at equilibrium, on that graph, which do you get more of, C and D or E and F? C and D. Okay, this is favored at equilibrium. That is said to be the thermodynamic product. It's the more stable of the two. Now, which is faster, the blue line or the red line? The blue line. This is faster, this is more stable. In this particular generic example, it is coincidence that the kinetic process is also the thermodynamic outcome. The faster reaction gave the more stable product. That will happen in many systems. The faster reaction can lead to the more stable product. Now, there will be other instances in which that's not the case. So on the right-hand side, some generic, A plus B giving C plus D, and also some other pieces E and F. Which is the thermodynamic outcome, CD or EF? Which is more stable? CD. That's the thermodynamic outcome. But for some reason, to be developed over the next 60 lectures, this one is faster but gives the less stable outcome, and this one is slower but gives the more stable outcome. They can switch. So the take-home message from that is it's about to get very complicated. Okay? Necessarily, heading to biochemistry, it's about to get really, really complicated. So if we're struggling in chapter 5, we're way past that now. We need to be in 6. Don't sweat too much about that. Just recognize that that's just me making a point. It's getting very complicated, and we'll try and point these examples out as we get there. Speaking of complicated, many of the pathways you will see are way more complicated than one step or 2 steps. They have multiple steps. By the time we get to the end of 3720, we'll have 10, 12, 13 steps in a mechanism in which A plus B goes someplace here, then someplace else, then someplace else, then someplace else, and eventually gets a product. That's much more complicated, but by the time we get there, you'll know what you're doing. So we have a more complex reaction profile, which is, in this case, multi-step. I don't think that word's on there, so let's write that down. Multi-step. How do you know it's multi-step? It has more than one reaction barrier. There's 1, there's 2, there's 3. You have different places on this graph that you need to be comfortable with. What is here? They are your starter materials. What's over here? They are your products. This is now showing that somehow the starter materials have to go here first and become something else, and then go someplace else and become something else, and then change again, and then get down to there. Complicated, multi-step. Go on. No, that's later. Yeah, but no. We've got to worry about the heights of these barriers. We've got to worry about the depths of these valleys and the heights of these hills. And we've also got to recognize that, for some reason, these things are in orange. This is the first time I think we'll define what's called a reactive intermediate. Something along the reaction pathway that is formed in a transient way and then reacts to go someplace else. So A might break apart into two pieces. One of them might be a positive carbon. And that positive carbon isn't stable, but it's formed, and then it reacts with something else to go to the products. That would be a reactive intermediate. So in this example, or in general I should say, typically these will be positive things, they might be negative things, and they might be radicals. Those will be reactive intermediates that are not isolated necessarily, they go someplace else. Mr. Santaganta, we could do some physics if you want, maybe that'll keep you awake. No. Questions? Okay. The first example of a real chemical reaction other than acid-base reactions which involves all these ideas. We're starting off with an alkyl halide. We're treating it with a halide ion, a different one, and they are reacting to swap out one for the other. You swap a reaction, you swap something, you do call what is called a substitution process. You're substituting one for the other. Substitutions are all chapter 7. So we are substituting the bromine for the Cl-, and we are producing over here the alkyl halide and the other anion. So basically we've swapped the negative charge from Cl and we put a negative charge on the Br. And it says here that this stuff is more stable. Okay. Which is more stable, Br- or Cl-? Br-, why? It's bigger. You already know this stuff. Bring it with you. And we are going now, mixing these two things together. And the mechanism here, be careful here, but this goes after this, and this gets kicked out. Why is this a fast reaction? This activation barrier isn't very high. I just said that you start putting things into the system, things can get slower. Why is this quite high? Why is this quite fast? Hydrogens are very small, yeah? Those hydrogens are very small. They're not blocking out that carbon. So that species Cl- can get at that carbon and start this process. And what's going to happen now as you go up this barrier, don't forget this, it's not a piece of string, it's the progress of what's happening, is that the chlorine's getting closer and you're attacking that carbon. Now why do you think we go up in barriers? Why do you think we're going up and not down straight away? How many electrons does that carbon have when we start? 8. And if you bring Cl- in with a pair of electrons, is that going to destabilize that carbon or stabilize it? Because it already had 8 and you're bringing 2 more in. That's a bad thing, right? And just jumping ahead a little bit, if I'm attacking this carbon and it's got 8 electrons in 4 bonds and all my bonding orbitals are full, where do I have to put my new electrons? Anti-bonding. Good, bad, or ugly? Bad. So is that going to stabilize the system or destabilize it? Destabilize it. So why we go up? Then it reorganizes itself and eventually gets to somewhere more stable. Now at the top of this barrier, this is more for chapter 7 next week, but I want you to be able to draw these pictures from scratch and things you haven't seen before if you understand the principles. So you're not going to be able to memorize this. What this is a good depiction. It's not a guess. We can calculate these things. We can't isolate these things. The difference between what's up here and what's down here is that we can isolate these things. We can crystallize them. We can distill them. We can't do that with a transition state because it's changing along the way. What we can do, though, is have a pretty good go at saying that this is forming and this is breaking. Why not just bring the bromine in and leave the bromine there and leave the chlorine there? Why can't you do that? 10 electrons, you're breaking rules. So if something comes in, something has to break off. Very much like an acid-base reaction. Now go back to the rate equations. This seems to be involving both CH3Br and Cl- at the same time. So if I add in more Cl-, do you expect the reaction to go faster or slower or stay the same? Faster. It's a biomolecular process in which the rate equation relies upon the concentrations of both this stuff, which we'll define next week, and this stuff. Both are in there. Now the key word on this slide is this: concerted. Everything's happening at once, in concert. It's a one-step process in which something comes in and replaces something else on a carbon. Much more detail on Monday, but this is all happening at once. How many reaction barriers on that graph? 1, right? A one-step process. One-step process there will be a concerted process. That's all there is to that. Go ahead. For the most part. I can't think of anything that wouldn't be. But of course, how many in the class are one step? If you have 1,000 reaction profiles in the class, how many do you think are one step? Maybe 2. Yeah? So let's get good at this quickly. I'm going to put homework 6 up today. I need to get that done today. So those of you who are keeping up can get on that and start practicing that stuff. I'll do the quiz due for next week sometime. So, John, as you were, presciently suggesting, this is a pretty complicated subject because reactions get more complicated. And the second big example in chapter 7, which is exemplified here, is a 2-step process in which something happens where this seems to break apart. If I put arrows on, it looks like I've lost my bromine. How do I lose my bromine? I break that bond. You can make this happen. We'll talk about details and how you make these things happen next week. But that thing will break off. If that thing breaks off, it becomes Br minus. And you generate this. And you've seen this before on the homeworks and in class. So what's the problem with that species? It's unstable. Why is it unstable? Carbon's only got 6 electrons. It lost a pair. So that's why it's here. It's an intermediate. It's quite high, but it's in a valley. And you might ask the question, well, what's the difference between up here, a transition state, and an intermediate? A transition state, the bonds are breaking and forming. It's a transient process between one thing and another. An intermediate is when that's finished. The bond has completely broken or completely formed. And it typically is something you can see, you can measure. We'll see how next year. So I've gone through a 2-step process involving collapse of this molecule to give what we call a carbocation, chapter 7. And this now needs some help. Where do you think it can get some help from? Say again? There's no catalyst in this mixture. We're not talking about catalyst at all yet. Chlorine, Cl minus. So Cl minus comes in, delivers a pair of electrons, and we end up over there. And next week we'll talk about why we have to go for second barrier. And it's all again the same idea. You're reorganizing the system. It takes time. It takes energy. That's why we go for that barrier. So how many steps in this process? 2. Certainly not 1. So therefore it's said to be stepwise. So far we've defined what a concerted process is, what a stepwise process is. You've got 125 reactions to worry about between now and the end of the 3720, and they all fit into these different categories. Ashley? So next week what we're going to say is that that molecule in this particular example is too crowded for that other process to happen. Okay? And this is where it starts to get a bit silly, because you come to class, you're half awake, you're talking to your friend, you're playing Angry Birds or whatever on your phone. I don't understand what he said today, because it is very complicated. I start going over here and over here and over here and over here, and I like this stuff, so I get all excited about it. If I drank coffee, I'd be dangerous, but I don't. And it's very easy to get lost. So get on it as soon as you can. Mark with a C. Well, let's keep that for next week. Let's save the good stuff for next week. These are facts right now. Under circumstances, some will go in one pathway, other circumstances they will go in this direction. That's chapter 7. This is setting us up in a very gentle way to get there. So I would argue I've got 2 different processes here now. Concerted, just the one step, stepwise, because I've got 2 reaction barriers. Every step will have a reaction barrier. So there's a lot in here now. I'm going to finish off today with something called the Hammond postulate, and then when we come back on Friday, I can get into this stuff. This will wake you up like nothing else. Dodson. They are transition states. I have not shown you their structures, and by Wednesday of next week, you'll be able to draw them in your sleep. Does anybody do this stuff in their sleep yet? I doubt it. By next week you will. Michaela.
So in the first one, it shows the bond forming. Why does it split? Like, is it?
Chapter 7. Chapter 7. I'm showing you that chapter 6 is before chapter 7. And that you should start, and to be honest, no, we're not being facetious. These are good questions because you want to be in chapter 7. So do I. We're setting you up for chapter 7. It's a teaser. Yeah? You like this, don't you, Joe? It's like getting there now. It's getting there. All right. So the last thing I'll talk about today, just to get people awake, is something called a Hammond postulate. This is a very clever but very, very useful idea. And what do these transition states look like? We're going to see them in detail. You're going to be able to draw them from scratch. You're going to have to draw them for things you haven't seen before. challenging, yes, but that's where we're at. The Hammond postulate says that the transition state, the thing at the top of the reaction profile, or each barrier, resembles the closest real species. Well, now we can talk about late transition states, we can talk about early transition states, we can talk about a lot more detail on these graphs. In this exothermic process, which is now not simply one step, is it? This could be part of a more complicated process. The reactants here and the products here suggest that the products are more stable. So at the top of this graph here, what does that look like? Does it look more like the starter materials, or does it look more like the products? What do you think? More like the reactants. Okay, it's closer in energy to these things, so Hammond suggested that most likely it looks a lot more like the starter materials. That will mean a lot in the later chapters when we get to the radical stuff. And on the other example over here, where it's an endothermic step, we have a transition state which will look physically more like the products. Why do we need this? Because we can't really measure transition states. We can't see them. They're transitory. Things are happening. Bonds are breaking and forming. We can't see that. So this is really useful to be able to get some idea of what those things look like. Go ahead. Yes. I'm going to bring this in next week in chapter 7 and get this in great detail. So let's be careful. Where are we going? We're going here. That is a fairly innocuous looking system that you talk about in second semester, and it involves a carboxylic acid reacting with an alcohol to give, in the presence of an acid catalyst, an ester, chemical change. That's how it happens. Now you can memorize this stuff. And I'm speaking to people who are not passing. I'm speaking to the people who are not taking the time to come ask questions and get things solved, because like it or not, you'll be taking it again. It's difficult. It is time consuming, but it also sets up things you want to do in the future. I can't memorize that. If you ask me to draw that out verbatim, I can't do that. It's a really big reason I don't do biology. I hate memorization, right? But as a chemist, which is where you're at, you can think about these things and you can come up with them and you can actually learn them. But this is the beginning of that. So if you're not getting onto stuff, get onto it now, or else it'll get worse.